Okay, welcome back to lecture 7b. Now we're going to look at the application of the momentum equation in an example of force on a pipe bend. Okay. We saw at the end of the last lecture a picture of a thrust block holding the pipe in place. Here is a particular example of a pipe coming down from a reservoir, where it's coming down and turning through this bend, and the act of turning the water through this bend changes its momentum considerably and results in a considerable force on this bend, which is a force acting outwards here. This bend just needs to be held in place, and here we see a concrete block doing that. That's tied into the stone of this mountainside, and it's this force Fr that we're trying to calculate. Well, it's actually Fr. Remember, is the force on the fluid. We're trying to calculate R acting out on the bend if we want to design that thrust block. Right, let's get started. First of all, we'll look at the problem. So here's a particular problem. This is a pipe bend that's got an area A1 at the start, and it expands and moves upwards, so we can see it's moving upwards, raising 1 meter until it's the area A2 at the exit. First thing to do is to draw a control volume. Now I've drawn a mustard coloured control volume here. Doesn't really matter, any arbitrary shape, as long as it encompasses the inlets and outlets. So I've got an inlet on the left and an outlet on the right. Choose a coordinate direction. Now it's a good tip to choose a coordinate direction so that either the inlet or outlet is in the direction of one of the coordinate directions. So I've done this here. Sensibly we'll put X in the direction of U1, and that means that we'll get more zeros in our equations and are slightly easier to use. So there's my coordinate direction, X and Y. We'll calculate a total force from our total force equation. Remember that, Ft equals rho Q U2 minus U1. Well, we have to resolve the U2 and U1 in the appropriate directions, X and Y. We'll calculate the pressure force, Fp. We'll see how that's done. We'll calculate the body force, essentially the weight of the fluid. And then we'll calculate the resultant force. Remember what our equation here is. We have Ft equals Fr plus Fp plus Fb, and we're going to calculate this Fr, the force that's causing the fluid to turn. So here's the example. Rising outlet from a pump, changing direction of 45 degrees. You see, identifies 45 degrees. Changing diameter from 150 millimeters to 300 millimeters. Remember to get the units right here. We're going to work in meters, not millimeters. We've got a pressure at 1 is 100 kilonewtons per meter squared, or 100 Pascal. Again, get the units right. We're going to work in newtons per meter squared, not kilonewtons per meter squared. So we've got the pressure at 1. Outlet is 1 meter higher. There's 1 meter higher. And the volume of the bend is 0.075 meters cubed. We're going to use that to calculate the weight of the fluid in the bend, so the force acting down. The flow rate through the bend is 0.3 meters cubed a second, or 300 litres per second. 0.3 meters cubed per second is the right units. And we're going to in the end find the reaction force R, which is equal to minus FR. Okay, right. It's often useful to calculate the areas and the velocities at the inlet and outlet right at the beginning of the calculation, because you're going to use them throughout the calculation. I've calculated the first area, 0.0177 meters cubed, and the second area is 0.0707 meters squared. I've done these to 3 significant figures. These are still very small numbers. I've done calculations, and the rest of the this calculation use numbers to 4 significant figures. So let's start by calculating the total force. So Ft here is rho q u2x minus u1x, which will be u2 cos theta 2 minus u1 cos theta 1. However, because we've chosen the direction of x in the same direction as the inlet velocity, we can drop the theta 1 and theta 2 and just use theta as at the exit. We've got q equals a1 u1 equals a2 u2, so we can calculate the velocities. We've got a pretty high u1 velocity, 16.98 meters per second, pretty high u2 velocities, reduced before, and that's what we'd expect. Always look at, see whether you'd expect that number to reduce, and you'd see because it's expanding, it's going to reduce. So we'll put those numbers into our total force equation, and I get here minus 4,194 newtons. So force acting to the left. In the y direction is our general equation, and as we've got y parallel to the inlet, the u1 term drops out. Put our numbers in here and we get 900.3 newtons. So it's a total force. Pressure force. Right, pressure force is the change in pressure force before phase 1 and phase 2. Or and we do this again in the x and y directions. So it's P1A1 cos theta, and theta is 0, minus, in this case, P2A2 cos theta, and theta is 45 in this case, which simplifies to that because cos theta naught is 1. And FPY, P1A1 sine theta, which is 0, that's going to drop out because sine 0 is 0, minus P2A2 sine theta, where theta is 45. So we're going to have minus P2A2 sine theta. We don't know what P2 is. We've only been given P1 in the question. We don't know what P2 is here, so we don't know what that is. How do we calculate that? Well, we know how to relate pressures a lot in a system. We use the Bernoulli equation, and here's our Bernoulli equation. Get used to writing that down. P1 over OG plus U1 squared over 2G plus Z is equal to P2 OG plus U2 squared over 2G plus Z2 plus any head losses due to friction. Now, the question says there's a friction can be ignored, so HF equals 0. Or we just cross this off in this example. So we're going to now calculate P2. There's a height rise between inlet and outlet of 1 metre. So if we take Z1 as 0, Z2 will be 1 metre, we can put that into our equation. It comes out for significant figures 225,300 newtons per metre squared. So the pressure forces, we put them on those, put the numbers in those two formulas from the previous slide. Minus 9,495 in the x direction, minus 11,260 in the y direction. So here's the significant numbers we're going to use. The body force, well, this is just the weight of the fluid, the force due to gravity. Always acts down. So it's going to be in the negative y direction. So we'll have an FBY, it's minus rho g times the volume. We were given the volume, it's 0.075 meters cubed. So using 9.81 for gravity here and 1000 for rho, density of water, we get minus 7,305. So minus 735.8 newtons acting down. So that's acting down. And in the x direction, there's no gravity in the x direction. It's acting. It's only in the negative y direction. So FBX is 0. So we can put all our numbers together here. We've got our two total force equations in the x and y direction. We can rearrange those to give us a reaction force, Fx. Put our numbers in and we get 5,301. And Fy, we put our numbers in and we get 12,900. Use the force diagram. So we draw the force diagram. And I always draw the force diagram so it's in the direction of the numbers, which is, as we've seen it before. We work out the resultant force. Comes out to be 13.95 kilonewtons, and the angle as defined on the diagram here, 67.7 degrees. Okay, let's have a look at the force on the fluid. There's our angle of 67.7 degrees, pushing up, turning the fluid around that bend. The force on the bend is in the opposite direction. That's the red arrow. So in these two lectures, 7a and 7b, we've seen a momentum equation, force on the bend, and we've seen an example of calculating that force on the bend. Thank you.